I'm recording. Excellent. So I'm going to now move on to the next set of slides. And let me look at my notes. Okay, so I'm a little behind, so I might like rush a little bit in some areas that I don't think are that important. And by that, I mean, I wasn't particularly good at math, I confess, but once I start learning it, I think it allows me to abstract so much. So I don't need to, I can generalize much better. So if you're like me, I assure you that learning the basics of machine learning, the basic theories and basic ideas, basic language that it uses, it's going to pay off by a lot. So I'm going to review three things. So I'm going to review some notation, matrix notation, a little bit of not even optimization, just some basic concepts of calculus like derivatives that will be used later, especially in deep learning, for optimizing and for learning, and some ideas about probability, expectations, and things like that. Okay, so usually in notation, we represent scalars as Greek letters. These are just numbers. Matrices are a two-dimensional array of scalars, and we say that a matrix has a certain number of rows, and that's the number of elements that you have going down, and a certain number of columns, so that's the elements that you have in the width of the matrix. And you can think of a matrix basically as a spreadsheet where you have n rows and p columns. Now, the notation that we usually use to access the elements of a matrix is this one. We use subscripts to access them. So this will mean the ith row and the jth column. Now, sometimes we represent our data as a matrix. So basically we say each of the rows represents the features of our subjects or of our journals or whatever we're modeling. It's just different samples, independent samples from the data. So we can think of with this notation, we can think of just a single index as saying, give me all the data that belongs to a single object. So a single data point in our data set. And that's going to be p-dimensional because before I said that, let's just say that we have a p-dimensional, p number of columns. So this will just return a vector. So you could represent the data of a particular data point with this notation. Now, usually when we talk about vectors, we automatically think about column vectors. Okay, so even though these really represents a row, so if I go back, this is a row of this matrix. When I just access one row, the convention is that it will be a row vector, a column vector. Sorry, it will be a column, even though in the matrix it's a row. Now we can also represent the features for all our subjects. So, and I'm borrowing here from the book, The Elements of Statistical Learning, and they use this notation. So if I use like a capital X instead of italic X and the column index, I will get the representation of that column. So this will get the jth column. I'm going to go back again. Sorry for the back and forth. It will represent all the data points, a particular feature for all the data points. Now, there are many operations with matrices, transpose, there are inversions. We won't really use them, I mean, in the teaching, but you have to be aware of certain operations that are standard. Now, the best motivation to learn about matrices and the properties that they have, at least to me, is because matrices represent linear functions. So you can think of, let's say, matrix multiplications as application of linear or more carefully affine transforms. So you can think of them as functions. So you can, there are these very beautiful connections between matrices and functions, so you can analyze functional and functional analysis with matrices. So so it's a very, very nice way of representing mappings between spaces. So when we talk about data, if I say we have a data set of n data points, I will mean that I will have a set of pairs. Okay, so this is in the supervised learning setting. I will have pairs of data points where I will have the features for each of my data points pair with an outcome that I want to predict. So this could be, we'll see later as an example that we want to predict the citations of a paper. X could be features such as the prestige of the author, the prestige of the institution, the prestige of the journal. Can we predict the citations of the paper only based on that? And how much explanation power just those three features have? So you can think of X as the collection of those three features and Y as the citation. Now, sometimes we have constants, so they're not variables, and we represent them with just Latin letters. And there are special matrices, and sometimes you can represent them very efficiently with this notation. You can say, I'm going to define the matrix implicitly by defining a function first and saying that I will generate the matrix by just evaluating each of the ij entries in the function. Now there are standard operations that you can do with matrices. If you multiply a matrix with a scalar, you just multiply each of the entries by the scalar, as we saw with NumPy already. Matrix addition, they have to be compatible in the size for this to happen. So there's this point-wise addition of each of the elements. Matrix multiplication, the number of columns of the left-hand side matrix has to coincide with the number of rows of the right-hand side columns. And this is a nice way of representing what the matrix multiplication is. And transposition, the same. You can represent it with this shorthand notation. And there are like countless, if you are into linear algebra, there are countless operations and identities that people have found about matrices that are very, very useful. I'm not going to go over them, but if you're a fan of these, there is all this this very famous cookbook that has all these properties that you can apply. And again, because it's connected with functions and even a lot of network science, you can think of the networks as matrices and connections as the entries in the matrix. You can think about connections and about properties of networks with matrices. But for that, wait until tomorrow. And we say that these are the usual way in which we represent the dimensions of a matrix. We can have the length of a vector, the size of a matrix, just going to be the Euclidean space of the Cartesian product of two real numbers, sorry. All right, so let's get into maybe something more concrete. So we will start with very simple models that relate inputs. And again, I mentioned the idea of predicting citations with outcomes with a simple linear combination. Okay, so I don't have an example here, but if you know graphs, usually graphs, you have, let's say you have a line, you have an intercept and a slope, and you can start to think about what those things mean. Okay, so let's take as an example the following very simple idea. So let's assume that I have the following statistical model that I learned from data, and I'm estimating the income of someone as being, and this is in dollars, let's say, in US dollars, starting from $20,000. And then every time you have 1 year of age, you increase your income by $5,000. This is very optimistic. But let's assume that we have this model, then we can take this and make predictions. Okay, we can say, well, if someone is born, right? So if the age is 0, we will predict that the person will be making $20,000. So already we are violating some assumptions of how life works. We can also think about the units. So the income supposedly is in dollars. So that's the unit of the income. So age here, I mean, this value here, 5,000, it's really expressed in the unit of the unit of income divided by age. So basically this 5,000, the unit should be, money divided by years, and then you have age in years. So when you have this multiplication, the units coincide. So that might be important later when you have multiple features in the same regression. You have to think about how to interpret the weights of your regression. So let's say if we want to make predictions for these three individuals, well, we can represent that prediction as a matrix of multiplication. So it's very intuitive. We can say, okay, the model that I learned has these weights. So it's just a linear model. I have the intercept or the bias term, and then I have the weight of the age. And my data, I'm going to represent it like this with dummy variables, so that when I multiply it, it makes sense. I produce the intercept, and then the second column will represent the features. So my predictions now will be very easily represented like this. I just multiply this matrix by the weights. Now, I can have multiple features, of course. So here I have age, and I can have education represented as, let's say, the number of degrees that you have. And I will do the same thing. I will represent the model as three weights. So I have the intercept or the bias term, the age term, the education term, and now the feature matrix will be the bias column and the column, one column for each of the features, age and education. Now, when we get to deep learning, we might look at how we optimize, how we can find the proper weights for our neural networks. And one way of doing that is by following the gradient of a loss function. So basically, we're trying to find the place where there is no change in the gradient. So we take our function, we want to find these places here where there is no, basically we find a zero in the gradient, there is no change. Okay, so if we look at the infinitesimal change of the outcome, the y-axis, as a function of the infinitesimal change in x, we want to see kind of the closest, the zoom-in line that we can fit to the function, and by looking at the places where that's zero, we can optimize. And we'll look at that in more detail later. But derivatives are very powerful ways in which we represent learning in machine learning. So this is the definition, and you can apply the definition to a function like this. Let's say I want to take the derivative of this function with respect to x. I can apply the definition, and if I derive it at the end, I will get b. And if you have training in calculus, you don't even need to do the derivation, because you know certain properties. So that's one of the nice things about derivatives, that you have all these derivation rules that you can apply very easily, and you can take the derivatives of very complex operations. Now, again, when we get to more complex, especially recursive functions, such as, well, here I'm not showing, but the chain rule. So here I have the combination of two functions, and for some reason I'm missing a parenthesis. So I'm gonna do live editing here. So if I have a nested function, I can still compute the combined derivative by just looking at the multiplication of the derivatives. Yeah, if anybody, yes, great suggestion. Thank you, Henry. So there's this channel that I love, 3 Blue, 1 Brown, that explains very visually what many of these concepts mean, and even they have on not deep learning, but neural networks. So definitely check it out. Thank you. And you can apply derivatives for more complicated functions, and there are very well-known forms for derivatives, especially when we deal with neural networks. But for now, let's just leave it like this. So this is a famous function in neural network called the sigmoid, and if you take the derivative, it will take a very nice form. So maybe let's leave this as a homework for you to do later. Okay, so In a statistical learning, we think that our results, the data that we receive, and the parameters that we learn are all stochastic. So there is a source of noise that doesn't allow us to know deterministically the actual values of those quantities. So probability is a field that allows you to quantify those uncertainties with a language that is coherent, that is mathematically correct. So so probability, if you want to learn about uncertainty and how your models are doing in terms of performance, then is the language that you should learn. Now, probability is a very unintuitive world, and I still fail to solve some very basic puzzles. So even after years of studying it, so just keep trying. But the easiest way for me to think about probabilities is to think about the frequentist approach. And if you're from a Bayesian camp, I'm sorry, but I feel like the easiest way to think about events in the space of probability is just to think about what would happen if I repeat an event an infinite amount of times. So for example, if I want to compute, if I want to understand the probability of an event happening, let's say I have a coin and I want to understand the probability of heads, of the coin coming up heads, it's useful for me to think about repeating that event, that experiment many times, and then just counting how many times out of all times heads comes up. Okay, so I'm not gonna now. We won't really need this much theory for probability. This is more like when you are dealing with perhaps with statistical, more heavy statistical learning, Bayesian learning. You might want to learn about these things, about set theory, but just think about probability as just a mathematical construct to represent uncertainty, and it has certain axioms that you can use to derive all the properties of probabilities. Okay, so I'm gonna so let's do this example, and by let I mean I'll do it here on the screen. So let's assume, let's think about the following experiment that I tossed two die. I have two dices, I don't know, although you have to say die. So you have 6 sides and each of them is equally probable. So let's say I asked you about the probability that the sum of the 2 die, it comes up to be 4. Okay, so you throw 2 things that have 6 faces, and you will do the summation of the outcomes of those faces, and I want to estimate what is the probability that I have 4. So the easiest way of doing this is, of course, to think about just listing all possible combinations of things. So we have 2, each dice has 6 faces, so we have 2 of them. So we have 36 possible outcomes in our experiments, just 6 times 6. And you can just list all of them. And here I don't have everything because it doesn't fit on the screen. Oh, now it fits. Okay, great. So I just list everything. And what I will do, I will add a column that represents what I want, which is a summation of the outcomes. And I will say, I want to see how many times I have a 4. So I have a 4 1 time, 2, 3, and that's it. So the probability of this event is basically 3 over the 36 possibilities. Okay, so random variables are a way of representing events in the real world. Sorry, it's a way of taking events in the real world into a function space. So you can think about, you can say this random variable represent an event, and you can start thinking about, okay, what is the probability of this what are the values of this random variable, and you will have attached uncertainty. So for example, you can do the following. You can say, okay, let's say I have the following experiment, and I toss a coin 5 times. So I want to create a random variable that represents the number of heads that I have in that experiment. Okay, so this random variable X represents that concept that I just mentioned. Okay, so there are two kinds of random variables: discrete random variables and continuous random variables. And as you might guess, this is basically discrete random variables. You represent events that can happen in a certain set that you can count. So you have a countable number of events that you can index, basically, so you can assign a probability to each of them. And the constraint of probability is that if you sum all possible events, countable events, you will get a 1. The total probability will be 100%. So coin tossing is an example of a discrete variable. You can represent the probability of heads, for example, with a discrete random variable. Counting, if you're, let's say, counting citations, that also will be a discrete random variable. It could be, 0 up to infinity, let's say, or a very big number. I'm going to skip some of these. Now, sometimes you want to represent uncertainty about continuous random variables, so variables that can take values in any area of the real line. So to think about probability in that space, in that sense, you have to think about slices of the curve rather than specific values. Okay, so it's not really correct to say, let's say, if you have a continuous random variable, to say what is the probability of a certain value. You have to think about the probabilities of a range of values. Okay, because the probability of one value is exactly 0 because there is no area under it. So it's really more like a density probability. That's the proper name that we give it. Okay, so I'm going to skip some of these. Now, the most obvious and famous probability distribution that is continuous is the Gaussian distribution. And here's the form in one dimension, and it has two parameters. It has a mean and a standard deviation. And here I'm showing different examples with different means. The mean, the parameter mu represents the mean, as it represents the point at which you have the most likelihood of an event happening. And the standard deviation represents how wide, how much probability it covers. Now, because the probability has to sum up to 1, so if I integrate all possible values from -infinity to infinity, because that has to be 1, if I increase the standard deviation, then I have to lower the curve. So I don't have so much likelihood for the mean, but I have to spread basically the likelihood across the real line. Okay. So for a lot of the things that we'll do in statistical learning, we want to understand the average error that we expect to see in a function. Okay, so we will represent our learning as a distribution. Okay, so we'll receive data and we'll learn about that data, and we want to see what is the average error that we expect to see in that learning process. And as a function, we want to understand as a function of the data that we have, as a function of the noise, as a function of the complexity of the model that we're using. So expectation is a really crucial concept in this space. Now, the way of thinking about expectations, to me, the simplest is to think about a fancy average. Okay, so if you take the average of several numbers, you add them all up and divide by the number of elements that you have. Well, in statistics, you can have now elements that have different values, like different probabilities, sorry. So you still can have the same lists, but you can attach different probabilities to them. So the way to compute this fancy average or statistics or expectations is to just take the values of your elements and just multiply them by the probability that they happen. So you can have now a differential application of your values. And everything falls down from there. So variance, kurtosis, all the higher moments, as they are called in statistics, they're just a result of the application of the expectation of some function. Now, sometimes you have multiple variables in a distribution. So let's say if we are representing the distribution of features that we have from our data set and the features in our example of citation, we can have, let's say, one random variable could represent the number of, let's say, the ranking of the journal. Another random variable could represent the prestige of the author, and another could represent the prestige of the affiliation of the author. So we can represent a three-dimensional data set as a distribution. If you have the joint distribution, so the distribution of all the variables, you can compute the distribution of a particular variable by simply averaging the joint distribution over the values of that variable that you don't want. In condition distribution, if you know something about something else, and we'll see this with learning, you can think about conditioning your probability by applying this operation. So you just take the joint distribution, you kind of renormalize it by assuming that you already know part of the space of events. If you have independent events, you multiply the independent probabilities, so the joint distribution gets simplified a lot. And that will be the end of this. So let's do a little activity. After all of this activity won't really take too many of the more advanced concepts, but I'll try to make it more intuitive. Okay. So this is the activity that I want you to work on. So let's assume we have this game. Someone proposed this game to you, and you want to see if it's worth playing this game. So the game is as follows. You have 3 coins. Let's assume they are fair coins, so the probability of heads is 50 or 50%. And the game is as follows. You are going to be paid $1. You will throw 3 coins, and you will get paid $1 for each head. Okay. But if you get all tails, you will have to pay the person who you're playing against $10. Okay. So the question is this game worth playing? Okay. So the easiest way to think about this is to simply just list all possible events and think about what is the expected value of playing this game. What are the expectation of the gains minus the losses of this game. Okay, so let's do again breakout room, and I will just recreate it because it's better to see other faces. Now you will be able to move around. So let's have 10 minutes to think about this problem. Any questions about this problem? Okay, so let's do the
one line.
Oh, a one-liner, yes.
Okay.
Okay, I'm gonna leave this open here on the screen so you can see. Worth means like if you're gonna make more money than lose money. Okay, so the expectation, basically you want to compute. Now we're not factoring the fun of playing this game. So it's the game minus the losses. Yes, that's a good point. I guess you are playing this game, so you're paid $1 and you have to pay $10 to the other person. It continues to work. Okay, great. 1 minus 10. So each of these events is equally probable. So I have 1/8 probability for each of them. So the definition of expectation, I have this function that we'll call G minus L. I'll just sum it. So you will take, well, the probability of the event. So the first event is 1/8. The function is G minus L, so that's 3. And then the second event is this one that has the same probability times 2, and so on and so forth. So you can see that at the end I can just factor that, and I have 3 1 time, 2 3 times, so 3 times 2, and then 3 times 1, and then 1 time minus 10. And then we have 3, so this will be 6. So 3, so that's 9 already, and this is 12. So I have 12 minus 10, that's positive. Excellent. So the game is worth playing. Yes, exactly, Ali. Thank you. Okay, great. Okay, so I guess we can take like a little break. Okay, so let's take like a 5-minute break, so that so that we can, a human, what do you call biological break. Let's do that. Recording. Okay, so now we're gonna get into statistical learning, and I might move a little faster if that's possible. All right, so we're just gonna start right off by trying to define what learning means. And my favorite definition of learning is from he's the head of the machine learning department in Carnegie Mellon, and he says that learning is basically using experience to improve future performance. That's a very machine learning definition, but basically you can think of this saying, okay, the experience that you have is data, the future is data that you have not seen, and performance is some way of defining what is good, what is a good, what will be a good error, how do you measure the mistakes that you're making. Okay, so you want to lower that in the future. So hopefully the more data you have, the more you learn and less mistakes you make. One of the challenges for when you're doing machine learning models, when you're creating them and evaluating them, is to know when you have extracted as much as possible from the data without risking basically learning from the noise, from things that are not really related to the outcome. So if you read the book on statistical learning that I suggested, the elements of statistical learning or introduction to statistical learning, they define it very simply as just techniques for doing supervised or unsupervised learning from the data. Very straightforward definition. Now, I will start by thinking about supervised learning. Okay, so in supervised learning, you have inputs, features, predictors, independent variables, whatever you want to call it, that are related somehow with an output, a label, a response, a dependent variable. And you want to learn a relationship between the two, so that when you see new features in the future, you can apply that relationship and predict or estimate what the output should be for that set of features. Now, usually, because, well, not usually, I mean, you have basically a supervision. So basically, you know what the outcome should be for a set of features. So it's relatively easy to say, okay, I'm going to measure the kinds of mistakes that I'm making by measuring the square error or the absolute mistake that I'm making, or something like that. You can define just arbitrary different loss functions or error functions. But in unsupervised learning, the only thing that you have is the features. So you don't have an output. You don't know how to relate those features with an output. So it's a much more complex setting. And if anything, the next frontier of machine learning, I will say, and artificial intelligence, is to develop develop better methods to make sense of data, and that means unsupervised learning. Most of the data is unsupervised. But for now, we'll focus on supervised. It's simpler to analyze and understand. So, sorry, my email open, close, it's making noises. So we measure features and want to predict an output. Okay, so we will like to identify what are the features and outputs in any of the examples that we see. And so here's one example I want to ask you, but I'm going to kind of make the example myself in my head. So let's say we want to predict, we want to establish a relationship between the citations of a paper in 2 years based on author, journal, and affiliation ranking. That's the problem that I was talking to you about before. So the features in this first problem are these elements here. So the author, journal, and affiliation rankings. So basically you have 3 features, and you want to learn or predict and associate those with the outcome. And the outcome is the citations that that paper will receive in 2 years. And you immediately can start thinking about what kind of problem this is, because citations, is a countable number. So you can think of a number of ways of doing this, but this sounds like a kind of regression problem. You can have something similar. So these days is very appropriate to not just think so much about citations, but maybe think about papers that are outstanding, that stand out of compared to other papers, for example, hit papers that break a certain threshold of citations. So maybe you want to predict whether a paper will be a hit. So based on the same factors, the author, journal, affiliation, you might want to make that prediction. So how can we learn that? Now, this problem is a little different in that the outcome of this problem is binary. So it's whether you break 50 citations or not. So you only have 2 outcomes. Sometimes you have other more seemingly impossible tasks, such as, let's say, predicting the key phrases associated with the publications based on an abstract of a publication. So this is a little bit more complicated in the sense that, let's say you have an abstract, a paper from PubMed, and in PubMed, each paper has associated generally a set of terms, and they're called mesh terms. And maybe you want to give it a new paper, you want to predict what the mesh term should be. So you have all the papers that have been published before, and you can say, well, I'm going to take those papers, I'm going to somehow process the abstract, and I'm going to predict, I'm going to establish a relationship between the text from the abstract and the mesh terms. And people have done this, but it's not so clear how you will transform text from the abstract and then how you will predict mesh terms. It could be variable. Sometimes no mesh terms, I think. Sometimes you have 5 mesh terms. So it's a variable prediction. So these are all forms of supervised learning. And the way that we will think about this is simply by trying to learn a function, or assuming that there is a function out there, mapping things from a feature space into an output space. Okay, so you have a feature space will be, let's say, the ranking of the journal, author, and institution, and the output space will be the citation. So the function will take elements from here. Each point here will be this 3-dimensional element object, and you will map it into the outcome. Okay? So you want to learn this function. Now, when you have the other problem, the predicting the hit papers, I'm going to make this smaller. Hopefully that works. The outcome is a little bit simpler. It's a little bit simpler in that you just have 2 outcomes. Okay, that you have 2 discrete outcomes. So it's a different type of problem. So the previous problem, where you have like a continuous space of outcomes, this is usually called a regression problem. And in this problem, where you have a discrete set of outcomes, this is usually called a classification type of problem. But they are both supervised learning. Okay, so I have data on this, and I will work with this data set on citations. I use MAG to compute this. So I have a set of papers, and I have the citations after 2 years. I have the ranking of the author, ranking of the affiliation, and the ranking of the journal. This is how the plot of that data looks like. Okay, so now this ranking comes from MAG. So they estimated it using well, they're using citations, so they're using, I think, the network of citations within authors to estimate the network of citations from affiliations and journals. So it's some sort of like an eigen value of the, it's like a page rank, sorry, of the, which I guess is kind of the same. It's a page rank of the author or journal or institution in the citation network. Okay, so the way that we will think about this in statistical learning, we'll say, okay, so we want to learn this. We want to learn this relationship. And what we do is we say, we will assume that this data is coming from a distribution. Okay, so we observe these pairs of X and Y, pairs of features about the paper and Y, which is a citation in 2 years. And we, with this notation here, I'm saying it's these pairs are being sampled independently from a distribution. Yeah, so every time I have a data point, we think about it in terms of we're sampling from the distribution. So it's a random process. Now, the problem, of course, is that we don't know this distribution. And if we knew it, then we wouldn't be a research question, right? So we don't know the distribution, so we need to think about this, and we need to do quite a number of simplifications for this. So the first idea is that we'll think about this. We will assume that the prediction of citations or any regression has the following form. It's assuming in statistical learning that we have, yeah, thank you for sharing that article. There are probably tons of papers trying to do this, and so it's still a very active area of research, and that could be a project too. So we're going to assume that there is a relationship between the features that we measure, and there is a function that maps that. But then when we measure the data, because we're sampling, we will assume that there is some noise, some intrinsic noise that is being added to the process. Okay, so it's as if we have the measures of the journal, and then because we are predicting 2 years ahead, right? There is some noise. You know, COVID happened, and everybody goes into COVID research, and we lose, interest in other research areas. So this noise could be all kinds of things. Could be, related to the system, related to how we measure things. Multiple sources of noise would perturb what we observe. So in reality, we assume that we don't really observe the real function f, but rather we observe the function f after some noise is added to it. Okay. Now, importantly, we assume that the noise is unbiased, in the sense that if we take the mean of this noise term here, the mean is 0. So if we get to observe the same set of features many, many times, and then we take the average, we are expecting that average will be around the same. So all the points are going to be very similar. We also assume that this error term is uncorrelated with the features that we measure. Okay, so this is uncorrelated errors. And this is an assumption that is not always true, but we're just making simplifications to understand what happens, what happened when we analyze the errors that we make. So there are two main reasons of why we want to estimate this function f. And in statistical terms, this is the words that they use, but in AI, they use different words. So in statistical terms, they say, well, once they try to understand this function, once they estimate it, they can make predictions, right? So if you understand the relationship between the factors about the paper and the citations, You can take a new paper and you can make a prediction about that paper that you've never seen before, and perhaps the features you've never seen before, but because you have the function, you will make predictions. Okay, so one factor is predictions. And in that realm, you care about the errors. Oops, the errors that you're making. How much errors? What is the range of errors? Are you making the best possible predictions? You want to kind of play that game of minimizing that to the lowest possible value. This is also so it's very practically useful. But there is another sense in statistical learning and AI, and that's the problem of inference. We want to understand what this function means, okay? And that can be different. So sometimes you want to make predictions that are really good. So you want to predict citations, for example, but you don't care too much about inference. You don't care about understanding why these relationships happens. You don't care about explaining to someone or writing a paper. You just want to make the best possible prediction. But if you care about inference, you want to interpret the results that you get. And here's where there are differences across approaches. Some approaches are much more straightforward to interpret and to do inference with, such as linear techniques. You can just look at the weights in the prediction and you can make estimations. And you can make interpretations. But there are other techniques that are much more obscure, such as deep learning, where it's really hard to connect the inputs with the outputs. So, so there is this trade-off between having a simple model versus a more complicated model. However, if you have a more complicated model, you have the ability, you have a budget to afford much more data. So that's why deep learning is so popular these days, because you can improve the performance significantly if you have enough data and you can constrain the model and the degrees of freedom that it has to make better predictions. So you have this continuum that, and I will show you a graph that shows basically, you know, linear models are here, the predictions are not that great, but the inference is great. Whereas deep learning is all the way on the other side. Predictions are amazing, but inference is poor. Okay, so this is the way that we will think about this problem. And what I want to do, I want you to think about how we evaluate how well we're doing this prediction. Okay, so again, we will assume that our true function is as follows. We have our observations, and we have a function that we never get to observe that passes through. I think all disciplines are covered, Sylvia. Someone is asking which disciplines are covered in MAG, and all disciplines are covered. And then you have some noise. But then you want to make an estimation. You want to estimate that F. You don't care about the noise. You only care about that F. You want to approximate it as close as possible. So we will be learning different functions of this form, different estimations. And this could be, again, regression, deep learning, it doesn't matter. This theory applies to everything. Now, one simple way of thinking about errors is just taking the actual value, well, the value that we have from our data, and subtract our estimation, our prediction, and square that. Okay, so this is a very, very straightforward way of trying to measure error, the square errors. So if we do this and we do some math that I won't go into, but basically this is if you understand a little bit more advanced estimation, expectation operations, you will realize that at the end, if you do this estimation of the error, you will get the following expression that is very important to understand. So the error that you will have in your model is going to be a combination of two things. You can see it right here. It's going to be a combination between how close you're going to get to the real function. Okay, so this is how close the f hat will get to a real function. So that's an expectation. Plus the variance of the noise. Okay, so again, let me repeat. The errors that you're gonna see in your model are gonna be a combination of things that you have control under. You have the control of deciding which function is this. So there is some hope that given enough data, enough computational resources, you will get to approximate this function as close as possible. but you will never be able to reduce this noise here because this noise is unrelated to the data. So there's no way you will learn about anything. And it makes sense. Think about trying to predict citations in 2 years. There are things that can happen in 2 years that you have no control under. And that's what this expression is representing. Now, in machine learning, this is called reducible variance, this term right here, and this is called irreducible variance, this term right here. So in the next couple of lectures or lecture, we're gonna look at ways in which you can understand whether you have any hope of reducing this part of the error, or maybe you have hit this part of the error. Is there any hope that you can improve your model, get more data, get more clever, get GPUs, I don't know, all kinds of things to reduce the error, or you just hit the most efficient way of making predictions. All right, so we have prediction. We want to reduce the error as much as possible. Let's move now on to why we want to estimate it, the inference part of things. Okay, so sometimes we want to estimate F because we want to understand what's going on. We want to say, okay, if the ranking of the journal is higher, then that means that we're going to get higher. Well, in this case, ranking, lower numbers means more prestigious journals in MAG at least. So you would expect to see a relationship that would look something like this, where you get to observe these points. These are the observations, but you can imagine this is not real, but you can imagine there could be like a real function that you don't get to observe that govern this relationship, and the function could be this blue line here. And maybe your estimation is really poor, it's just a line with red. This red line could be your estimation, your F hat, but you can still use this to say, well, the higher the ranking, the lower the citations you're expecting. Okay, so you want to estimate things, and how do you estimate it? Well, that's you will propose a model. You will say it could be a linear model, it could be a deep neural network, and you will estimate the parameters of that model so that you fit the training data as close as possible. So I'm gonna kind of skip this a little bit. This is more theory about how you estimate the parameters. You don't need to worry about it too much. Most of the techniques that we see in the wild use more of a frequencies approach, where you say, okay, this is the parameter, the set of parameters that predict the best. But there is another approach called the Bayesian approach, where you have a distribution of parameters. Okay, so we can look at a very, very simple example. We want to just understand the distribution of citations. So this is the distribution of citation for the data that I was showing you. And we can say, okay, let's assume that this is a Gaussian distribution. It's a very poor approximation because the Gaussian distribution has two tails, but citations is a count random variable, so it's not the greatest approximation. But you can immediately see if we approximate the citations with a Gaussian distribution that we want to put the highest possible value on top of the peak of the citation distribution, and maybe make it that it covers it, so it maximizes the likelihood of observing the data. So you can do the math, and you can see that the solution at the end will be relatively straightforward. I won't do it here, but because also this problem is not very interesting. What we're really interested in is relating some features that we observe X with the citations. So the way that regression does is by saying we're going to have a linear function. So I will take my features and I will multiply each of them by a value, and then I will add Gaussian noise in the prediction. That's the assumption that I make. Okay, so if you make that assumption, then you get solutions such as this. So to find the best possible parameters, you have to the solution that is a standard, well-known form to get the parameters that will minimize the error, the square error in your regression. So so basically, you're trying to find the line that will minimize the difference between the real value, the square difference between the real value and your prediction. So I'm going to move along here a little bit. So if you add all those square errors and you take the average, that's called the mean square error. And so we can propose this is our estimation. This is our model. We don't know if it's linear or not. Probably it's not linear, but we can make this assumption and ask scikit-learn or another package to find these parameters for us by optimizing. Okay, so it turns out that the best parameters are this. Okay, so this is based on MAG. I have the other notebook that does this. So the best parameters that I found was, you predict that the best possible ranking will produce 100 citations on average after 2 years, and then it will go down by 0.005, and you can see that there are like 20,000 journals. So it's a linear decay. Well, not linear decay. We're assuming that it's a linear decay, but as you can see, the actual data is much more complicated. Okay, so so that's regression. Now classification is the same idea. You can assume, I'm going to skip this. You just can assume that instead of being a Gaussian distribution as an outcome, you can assume that it's another distribution that has just discrete outcomes. And for a regression, for a classification such as this one, the hit paper classification, you can assume that the outcome is a distribution known as the Bernoulli distribution. Okay, so this is the data from trying to relate the ranking of the author. Again, this ranking is based on a page rank kind of ranking that MAG is applying, and whether the paper will be highly cited. And as you can see, it's a little unclear, because the data is all over the place. Most of the papers, of course, are not highly cited. And there's quite an overlap based on the ranking of the author. But it seems that if you squint, you kind of look at it carefully, maybe there is some relationship there. Okay, so this is the graph that I wanted to show you. Like if you look at regression, at linear regression and logistic regression, those models are relatively easy to interpret, and they don't have a lot of flexibility. They're not very accurate if you compare it to more complicated models. So if you move into more complicated models such as Bayesian boosting, if you have heard of random forest gradient boosting, those are much more complicated models that can fit very complicated functions, but they have but they are not very interpretable. So it's really hard to tell, the relationship. Yeah, it's not based on theory. It's just made up from the authors of the book. And deep learning will be even more flexible and even less interpretable. In fact, there is an entire field called fairness in AI, and Lijian, will talk about some of his research on interpreting deep learning models. And it's quite difficult. People are struggling. As you know, these models can make biases, and it's really, really hard to detect them. Okay, so unsupervised learning is much more complicated because you don't have a relationship between a feature and an outcome. So what you can think of unsupervised learning as trying to just learn an intermediate space where you can represent the data more compactly. And we'll see a couple of those examples with PCA, clustering, topic modeling. Okay, so let's do an activity. And the activity will be relatively simple because it was a lot of theory and things like that. Definitely go back to it. But I want you to think about supervised and unsupervised problems in science of science, and think about 3 problems in science of science that require different kinds of predictions and inferences. So remember that predictions are problems in which you care about how little mistakes you're making. But because there is this fundamental trade-off, the more you care about the errors, the more you want to minimize the errors, the less interpretable your solutions are going to be. Okay, so there is this intrinsic conflict between the two things. So there are some set of problems that require really, really good predictions, but you don't care so much about what they mean. There are problems that you really care about what they mean, and you don't care too much about the quality of your prediction. And there are problems where you care about both. Of course, you would like always to have these, but why don't you discuss with your breakout room team these problems, and then we can share them. Any questions before that? Okay. So let's do, this should be a little shorter. I'm going to do 5 minutes. Okay. What would be an example of a supervised problem? Okay, David says unsupervised recommender systems as a question. Interesting. What would be a recommender system? Field delineation, right? OCR can be supervised. Supervised topic modeling. Okay, so let's take these examples. Now, unsupervised, unsupervised means that you don't have an outcome that you want to predict. So in recommender systems, do you think that's happening? Unclear, because let's say if you are in Amazon, like they use your previous purchase information to recommend papers. You use MAG, or you use, I guess if you use Semantic Scholar, I think they keep track of what you liked before. So they are trying, it's like a semi-supervised approach. OCR can be supervised, right? Because you can have, let's say, an image, and you might have someone, a human, who annotated it, so you know what, I mean, at least the human level performance of what the characters should be, where, and what are the words, and you can try to learn a mapping between the image, the pixels, and those characters. Predicting the novelty of a paper, supervised. Yeah. Now, to make it supervised, predicting novelty, that's very interesting. To make it supervised, you will need kind of someone to tell you that a paper is novel and maybe find that relationship. That's one way. The other is like but the common thing in which people do it in novelty detection is in unsupervised manner. They just learn that, okay, I'm gonna just compute something that is like outside the standard distribution of things. It's like an indirect way of measuring things. Yeah, recommender system can be reinforcement learning too. Yeah. Clustering authors, yeah, that's unsupervised. Now, topic modeling, someone mentioned topic models. That's usually considered unsupervised in the sense that you don't really know what the topics of the papers are. Most of the time, you don't really know, unless you have maybe a specific data set where people have clustered papers into topics or ideas into topics beforehand, and you're trying to reproduce that. But generally speaking, you're just trying to cluster. You don't really have a ground truth way of knowing what the right cluster is. Predicting reason of citation. Yeah, supervise with annotation from experts. Yeah, that will be interesting. If you have a data set on that, that would be awesome to have. Okay, what about the next? Now, I'm interested in hearing, now, prediction and inference, like caring about those two things, this is obvious. Everybody wants to have excellent performance and have excellent interpretability and inference. So this is not that challenging. I'm interested in knowing examples where you think this is the fundamental, this is of the utmost importance. Which problems in science of science are prediction, but you don't care so much about inference? Topic modeling. Okay. Recommender systems. Most NLP are actually very much supervised. Yeah, so to have prediction, you need to have a way of measuring performance, and usually means supervise. I don't know about topic modeling, because in topic modeling, I don't know which kinds of things you are thinking about, Bilal, but usually in topic models, you want to interpret things very well. You have texts and you want to understand what those texts are saying. And unclear how to measure performance because unless you have supervised data. Predicting topping over time, right? Now we don't care. I mean, in science of science, I would say that this is not really the ideal case. We don't really have a problem. Let's say if we're trying to understand citations, yeah, you might care about, you want to make the best possible prediction, but what's really perhaps more impactful is to know why something is happening, the inference side. So I would say I've seen papers using this like deep learning for predicting citations or something like that. But for the most part, when you're doing analysis, you want to have like models that are interpretable. You want to understand what's happening. So I would say we care a lot about things like this inference without caring too much about prediction, I would say. Disambiguation is a very, very tough problem. And I would say we probably want the highest possible performance in disambiguation. We don't care too much about how it's doing it, right? So I guess. Okay.